So enough of that nasty review stuff. Let's talk about coordination compounds. Now, coordination compounds consist of two parts. You have a metal, usually in the form of a metal cation. In fact, just about everything we're going to study today, the metal is in the form of a cation. That's why it's important that you followed the oxidation states that we talked about earlier. Now, metal cations, of course, they're positives. They like to accept electrons. That means that they are Lewis acids, right? Lewis acids are electron acceptors. Okay, you could also, of course, if you wanted to go back to your organic chemistry, say that the metal cations are electrophiles, but I don't. I call them Lewis acids. Okay, now, of course, Lewis acids like to react with Lewis bases. Okay, Lewis bases are electron donors. So if our cations are acids, the donors can be anions, they have extra electrons, or it can be a species that has a lone pair. But anyway, when you put those together, a Lewis acid base complex, the metal cation that wants to accept electrons, the Lewis bases that want to donate electrons, you call in this particular case those Lewis bases ligands. Okay, so we're going to be focusing all the way through this on the two bits of a coordination compound, the metal cation, the Lewis acid, and the ligand, the Lewis bases. We spent a lot of time talking about the metals in the previous set of videos. So let's think about things that can be ligands. Remember, these are Lewis bases. They're going to be electron donors. And you need to be able to recognize a lot of these ligands and some other funny things about them. Now I'm going to split the table up into two parts. First of all, let's look at neutral ligands. Okay, so these are ligands in which you have an atom that has a lone pair that can act as an electron donor. So ammonia is a great ligand because that nitrogen has a lone pair. Water is a super ligand because, of course, the oxygens have two lone pairs. But there's some other important neutral ligands that you need to be able to recognize. Carbon monoxide, you don't think about carbon monoxide doing much, but that carbon has a lone pair of electrons that it's quite happy to donate. The oxygen, of course, also has a lone pair of electrons, but the oxygen, more electronegative, likes its electrons better. There's some other factors at work there too, but essentially the carbon's lone pairs are the ones that will donate towards the metal cation. Sulfur has a lone pair of electrons, so dimethyl sulfide is a good one. Lots of nitrogen containing ligands. Here's another good one, pyridine. That nitrogen has a lone pair of electrons. Phosphines, though, phosphorus with two electrons on there. Remember, phosphorus is in the same group as nitrogen, so lone pair of electrons. Phosphines, and I've got two examples here, trimethylphosphine, where you've got phosphorus with three CH3 groups, triphenylphosphine, where a phosphorus with three phenyl groups on. And remember, phenyl group is a benzene ring as a group. These are really important ligands when you get into so-called organometallic chemistry. So nice set of neutral ligands that I want you to recognize, and also notice some of the special names given to them. When you have ammonia acting as a ligand, it's called amine with double M. When you have water acting as a ligand, it's called aqua. Okay, when you have carbon monoxide acting as a ligand, it's called a carbonyl ligand. And here are some anionic ligands, some of them very familiar to you. There's bromide, chloride, iodide, fluoride stuck in there, so your halide ligands, hydroxide, OH-. Cyanide, of course, that you've seen quite often associated with your organic reactions. Cyanide is often called a pseudo-halide because a lot of things that the halides do, cyanide will do as well. Another pseudo-halide is azide, N3- that we've touched on a couple of times in our organic. And then some other ones that you might not have seen too often. Methoxide, these are the anions that come from alcohols. When alcohols act as acids, they make methoxides as their conjugate bases. Alcohols are, of course, ridiculously, pathetically weak acids. They're hardly weak acids at all, which means, of course, methoxides very strong bases. And you can't just have methoxide. We could have ethoxide with the ET there. We can have tert butoxide. Those of you who know how much I love the tert butyl group, that's an oxygen to a carbon that has three methyls and so on. All of these are good anionic ligands. And then thiocyanate, which is an awesomely good one. Thio, of course, means that you have a sulfur in there, and the thio in this case is replacing an oxygen, so it's thiocyanate. Now you can have sulfur that has a lone pair and nitrogen that has a lone pair. And it can act as a ligand through each of these, and we'll talk about that in a minute. So essentially, here are the names of them. By and large, the way you're supposed to name the anions is you take the name of the anion itself and replace the E with an O. So you can see that azide becomes azido, thiocyanate becomes thiocyanato, methoxide becomes methoxido. Some of these sound a bit stupid, so a lot of times you'll actually use the older names. So for the halides, it's not bromido, it's bromo. It's not fluorido, it's fluoro. Hydroxide is not hydroxido, it's hydroxo, and so on. So anyway, be familiar with these names, be familiar with these ligands. And these are called monodentate ligands because they only have one atom that's going to be an electron donor to a metal at any given time. You might have more than one possible atom, like with thiocyanate, but it's only going to be donating to one metal atom at a time. That distinction is important because there's another very important set of ligands called polydentate ligands, right? Now, dentate means teeth, so polydentate means that you're having more than one bite, more than one atom can be a ligating atom in the ligand. So we can have bidentate, which are probably the most common. Bi meaning two, so we got two donor atoms, two Lewis basic atoms in there. Really nice one that I love here comes from oxalic acid. Oxalic acid is the simplest dicarboxylic acid. You lose the two acidic protons on it, leaving you behind with O minus to make what I call the oxalate anion. Fancy people would call it ethane dioate anion. Its abbreviation is OX. So anytime you see OX in a transition metal species, you know it's a 2- anion, and that's very important. And you know that it has two oxygens bonded to the same metal. Another similar one, a very important one, ACAC. All right, the old name acetyl acetonate, the fancy new name pentane 2,4-dienate. When those act as ligands, remember they're anions, so you'll lose the E for the O. So this would be acetyl acetonato or pentane 2,4-dienato. Much easier just to call it ACAC. We have quite a few neutral bidentate species that are very important. Neutral ones because you've got the nitrogens with their lone pair. So this one here, two nitrogens separated by two carbons there, is called ethylene diamine or ethane 1,2-diamine or N for short. This one here is similar, propane 1,3-diamine. You can see you just got an extra carbon atom in there called PN for short. Very important class of bidentate ligands are those in which you have pyridines stuck together. So that's an aromatic ring, but one carbon has been replaced by a nitrogen. So you can see here two of the nitrogens there in this 2,2' bipyridine or BIP for short. And then this one here, 1,10-phenanthroline. Again, you can see the two nitrogens there as part of aromatic rings. That's called phen. So some really, really important bidentate ligands that you need to look at. Now, something that's rather important is if you think about the metal atom here, okay, that metal atom, you can see my little dot, when it's bonded to those two oxygens, it's going to make a 5-membered ring. Okay, metal atom is a little dot bonding to the two oxygens, that's a 5-membered ring. Here we would have a 5-membered ring. Here we would have a 5-membered ring. Here we would have a 5-membered ring. 5-membered rings when you include the metal and the ligating atoms, very, very stable. Also very, very stable, 6-membered rings like we see with ACAC here. Take the metal atom, that's my little dot, bonded to both oxygens, and you can see it's part of a 6-membered ring. Propane 1,3-diamine, put my metal dot here, part of a 6-membered ring. Bidentate ligands or polydentate ligands generally are going to be really cool and stable. When you bind the metal, it makes it part of a 5-membered ring or a 6-membered ring. Now you can have more than bidentate. There's a few tridentate ligands I want to show you. This one here, that's essentially a couple of N ligands, ethylene diamine ligands fused together to give you 1,4-triazoheptane or diethylene triamine. abbreviation is DIN. Just quickly showing you where these come from. The old name ethylene is a CH2CH2, so that's that 2 CH2s there. So here it was 1 ethylene, here we got 2 ethylenes bonding the 3 nitrogens, the triamine. A lot of times when you will name these, when you have nitrogen in a ring, you can name it by giving the same number of nitrogens in a chain. You can take the same number of atoms in the chain. So 1, 2, 3, 4, 5, 6, 7 is heptane, but 3 of them are nitrogens. Aza is the way you say nitrogen, like thio is the way you say sulfur. So 1,4,7 triazaheptane is 7 atom chain in which the first, fourth and seventh, so first, 2, 3, 4, 5, 6, 7 atoms are nitrogen atoms. You're not going to be quizzed on that. It's always good to see where some of these silly names come from. Anyway, the fancy name for that is not just 1 N, it's a di-N, 2 N's, because you've got it as a tridentate ligand. Again, though, think about where the metal's going to go. If it bonds to those 2 nitrogens, that's a 5-membered ring. Bonds to those 2 nitrogens, 5-membered ring. You can have some of those aromatic pyridines joined together here. So this was bippy because you got 2 pyridines. This one is terpy because you have 3 of the pyridines. Remember, ter is a silly way to say tri, but tripy is not quite as silly as, or is sillier than terpy by only just a little bit. Again, don't worry too much about where some of these numbering schemes come from. Just be familiar with it being a tridentate ligand. Again, metal can go here, making a 5-membered ring here or a 5-membered ring there. And then the last one that I know you've heard of, big sort of granddaddy of polydentate ligands, a hexadentate one right here. The oxygens of these carboxylate groups, little minus there, they've lost their H+, leaving behind O-. That's 1, 2, 3, 4 atoms that combined, and then the nitrogens each have lone pairs, so 5, 6. So hexadentate, diamino, 1,2-ethane, N prime tetraethanite, otherwise known as ethylene diamine tetraacetic acid, or tetraacetate is what it actually comes to here, or known as EDTA. Okay, it is the 4- ligand generally, and it's really cool because, as we will talk about in a later movie, it can just wrap itself around the metal ion, completely filling that metal ion, protecting it and binding to it in a very, very strong fashion. So some ligands that I want you to become familiar with: string of monodentate, and now some really pretty pictures for the polydentate ones.